In the last lecture, we considered a solar air heater of typical configuration, which consists of a duct and one glass cover, and then bottom is insulated. A fluid flows at a rate of m dot, entering at T f I and exiting at T f O. We considered the energy balance. On the absorber, bottom plate, and the fluid. So, two cases we considered, u b to be less than u t and u b not neglected. We will get in terms of a overall loss coefficient, which is expressed in terms of u t and u b and other heat transfer coefficients. And finally, q u can be put in the same form as A C F R into S minus U L into T F I minus T A, though calculation of U L will depend upon the heat transfer coefficients and the top loss coefficient and the bottom loss coefficient. Subsequently, we tried to calculate the heat transfer and the pressure drop and flow is assumed to be turbulent conditions, fully developed, which we have defined in U invariant with x, and so is some temperature non-dimensional. And this is a case of one of the walls of the duct being subject to a heat flux and the bottom being insulated. We found for a case of let us say 1 meter long by 1 meter by 1 centimeter cross section. This is cross section. Okay. A L by d E, it turned out to be about 50, which satisfies greater than 30 for fully developed condition. There are two correlations. One is due to case, where the Nusselt number is expressed as 0.0158 R e to the power 0.8, where Nu and Re are based on hydraulic diameter. Another commonly used correlation is due to Malik and Bulow, which gives Nusselt number So, of course, the equivalent diameter or the hydraulic diameter, which we have already defined as d E or d h, is 4 times the flow area by wetted perimeter. And we also set H 1 and H 2 are considered to be equal. Okay. Also, the properties are evaluated at T f mean equal to T f I plus T f O by 2. If the fluid inlet temperature is T f I and the exit temperature is T f O, the mean temperature is T f m, given by just the arithmetic mean T f I plus T f O upon 2. So, the property values like thermal conductivity K, kinematic viscosity nu, and if necessary density rho, all of them are calculated for the fluid at the temperature corresponding to T f m. Now, we come to a more important thing. First, we are considering the air heaters vis-a-vis liquid heaters. The advantage for the air heater is in the direct application of hot air, which the solar is likely to meet very conveniently, because the higher temperatures are not very high temperatures are not required. Something like 40 to 60, 70 degrees centigrade is good enough for quite a few applications. Then secondly, air compared to liquid in general, your heat transfer coefficients are low. Relatively, you can say that if the Nusselt number is the same, since the thermal conductivity of air is considerably lower than the thermal conductivity of liquids or water, you have a lower H. Consequently, it operates at a higher delta T. In other words, if the air is to be at 60 degrees C, probably the absorber temperature may be 80 compared to a 70 or a 65 for a liquid based liquid heating system. In addition, to compensate that, there are other methods which we will briefly touch upon in the later part of the lecture. And if you consider the flow rate of, or let us say, water and air for a given energy gain, at least approximately, Q dot air volumetric will be approximately 4 times Q dot water volumetric times 1000. You can see the specific heats of water and air, they have a ratio of about 1/4. Okay. The specific heat of air will be 1/4 that of water, and the density is 1,000 that of water. So, if you calculate for a given MCP delta T, you need to have a volumetric flow rate of about 4,000 times or a mass flow rate of 4 times that of a corresponding liquid or water heating system. So, that is one reason you do not have tubes in the case of air collectors, most of the time they are ducts. So, in the absence of a high heat transfer coefficient, there will be many techniques. Somebody may put fins or obstructions or turbulence breakers or flow breakers to enhance the heat transfer coefficient, but right now this is not our objective. That again will increase the pressure loss, thereby in spite of the fact it may gain a comparable energy as that of a liquid heater, you may have to spend more pumping power, and pumping power is a higher grade energy, which will require a 4 times or 3 times the thermal energy through a coal burnt or somewhere, etc. This is one aspect one has to keep in mind while designing the air collector systems, which will again come to it little later. Now, the friction is calculated from the Blasius formula. So, this is pressure drop in the, this is F is the friction factor, this is due to Blasius, the famous 1/4 power law. This is also at the equivalent diameter. D or D naught. Now, this is in turbulent flow category, valid for smooth surfaces. So, this is what we have here. So, we have methods to calculate or the formula to calculate the heat transfer coefficients in the air ducts and the friction factor, and hence calculate the pressure drop in the air duct and find out the pumping power needed and compare with the energy gain, and make sure that the energy gain is significantly more than the pumping power required. So, the configuration that we have considered is a duct in a box and then one glass cover. So, the absorbed energy over here is transferred to the fluid, then also by radiation and again convection to the bottom, and then some loss from the bottom. So, you may call it to cut down the cost, or anyway rectangular passage is needed. A simplified configuration is designed, another configuration that let us call it like that. One glass cover, one absorber plate and insulation. The flow is perpendicular to the plane of the paper. In other words, the duct is formed by one absorber sheet and one glass cover. Obviously, if we put them side by side, This is the first configuration and this is the second one. With only one absorber. Flow is through this and flow is through this. Obviously, here the higher losses. This being hot air is directly in contact with the top radiation and convection losing surface glass cover. Whereas, here at the absorber then there is free convective loss instead of a forced convection loss. So, this is expected to be better. So, this may become comparable to something like this. Only one absorber plate formed between one glass cover and another glass cover. These two may be equivalent, whereas this may be slightly inferior. However, there are many issues whether one glass cover or two glass covers from the weight point of view, transport point of view and maintenance point of view. So, this is what we had discussed in detail. The top loss coefficient will not be the overall loss coefficient. If the heat transfer fluid comes in direct contact with the heat losing surface, this is one such case, because technically apparently the loss from the absorber also goes to the fluid, which is the useful energy gain. So, we will show one such configuration which I have already shown. This is the insulation. This is the top glass cover at a temperature of T c. This is at T p. The fluid is at T f with H 1 and H 2 as heat transfer coefficients. Flow is something like this, and this is a U t, and you have got a U b, and this is my absorbing plate. So, we can write down straight away the radiative heat transfer coefficient between the plate and the absorber will be sigma times T p square plus T c squared times T p plus T c by 1 upon epsilon p plus 1 upon epsilon c minus 1. This is nothing but H r into T p minus T c is equated to sigma times T p to the power 4. Let me write it down. H r into T p minus T c equal to sigma into T p to the power 4 minus T c to the power 4 by the normalized emissivity epsilon p plus 1 upon epsilon c minus 1. Okay. If you do that, take T p minus T c onto the other side, you will get H r of whatever we have written here. So, how does the thermal network look like? So, let this be the fluid temperature T f, from which useful energy gain comes. Then we have got 1 upon H 2 losing by convection to the absorber at T p. Then from here to T c, the cover temperature, with 1 upon H1 as the resistance, and then Ta with a resistance of 1 upon Ut. Of course, you have got a S absorbed energy over here. The loss is from here to here, which is upon of course, with a resistance of 1 upon Ut. Okay. Now, you have the energy balances. This is UB. On the cover, HR times Tp minus Tc plus H1 into Tf minus Tc should be equal to Ut into Tc minus Ta. So, by radiation it is from the plate to the cover, and by convection from the fluid to the cover, assuming this is what the cover is receiving and it is lost to the environment given by Ut into Tc minus Ta. Then plate, this we will call it an equation A. On the plate, absorbed energy S minus the bottom loss Ub into Tp minus Ta minus H2 into Tp minus Tf. So, it is a loss apparently, or gain if Tf is higher. Tp minus Tc should be equal to 0. So, this is the absorbed energy, out of which bottom loss is going this much, and this is from the plate Tp to the fluid is received. So, this is gone out of the incoming, this is actually the useful energy gain minus the radiative loss from Tp to Tc. Then the fluid H2 into Tp minus Tf minus H1 into Tf minus Tc should be equal to Qu. So, this receives from the plate temperature Tfp to Tf and loses from the fluid temperature Tf to the cover temperature Tc. That net should be equal to the useful energy gain Qu. So, these three equations are solved in terms or to express Qu in terms of Ut, H1, H2, HR, Tf and Ta. So, from A, that is the cover, and B, the plate, and C, the fluid. Just for our easy reference. So, from A and C, you will have long equation Tp minus Tf equal to S times Ut plus Hr plus H1 minus Tf minus Ta times Ut Hr plus Ut Ub plus Ub Hr plus Ub H1 upon Ut plus Hr plus H1 times Ub plus H2 plus Hr minus Hr square. So, this we will call it D. So, Tc minus Tf equal to Hr into S minus Tf minus Ta times Ut Ub plus Ut H2 plus Ut Hr plus Ub Hr by Ut plus Hr plus H1 times Ub plus H2 plus Hr minus Hr square. This we will call it E. You may be wondering all these long equations whether they can be remembered. It is very difficult to remember, and I will also strongly suggest you please work out the algebra and check these things, because I have the benefit of seeing it on the computer screen while copying, but then with so many subscripts there may be a mistake, and ut, u1, uh they look little confusing, but I try to be as careful as possible, but nevertheless you can check it with either standard textbooks or you work out. There may be one or two differences that you can easily figure out. So, on substituting, for example, you can always refer the textbook by Duffy and Beckman. Nevertheless, you have to work out, because the details are not given in most of the books, because this is a laborious algebra. So, what really matters is your Q is f dashed times S minus U L into T f minus T A, where f dashed is H r H 1 plus H 2 U t plus H 2 H r plus H 1 H 2 upon U t plus H r plus H 1 times U b plus H 2 plus H r minus H r square. And the overall loss coefficient U L is another big equation, U b plus U t times H 1 H 2 plus H 1 H r plus H 2 H r plus U b U t times H 1 plus H 2 by H 1 H r plus H 2 U T plus H 2 H R plus H 1 H 2. Okay. So, this will be good to solve and difficult to remember. So, consequently most of the time from students point of view this type of a question will be more suitable for open book exam rather than a memory test. Now, you can see from this equation U L is not equal to U T even if bottom loss is 0. So, this is where it comes that the fluid is directly coming in contact with the top of glass plate where from the loss is taking place, and whatever the fluid is receiving, if you look at from the plate point of view, it is a U T into something or a heat transfer coefficient into T p minus T f, which is also the useful energy gain. So, if we want to have a summary of the flat plate collectors, we have considered typical liquid and air heating solar flat plate collectors. One is the fin and the tube type of absorber, or like this, liquid, for air a duct with one glass cover, and the bottom insulation. And the next configuration was with only one absorber sheet and one glass cover, and the flow channel being perpendicular to the plane of the board, here and here between these two. This is insulated. So, this is air heater 1, this is air heater 2. So, first we did it with the framework of steady state analysis, then we made transient analysis. This is particularly to calculate warm up period. The basic idea is the collector, covers, absorber, they have to reach certain temperature in order that they are able to give energy at the desired temperature from the fluid coming out of the collector. Otherwise, the temperature if it is lower, the fluid cannot be heated up to the temperature. In addition, we briefly considered the concept of critical radiation level, where the useful energy gain is 0 for a certain temperature of the absorber or the inlet fluid temperature. Consequently, the solar radiation intensity has to be above the critical level in order that it supplies the energy at the delivered minimum temperature desired, and before that the collector should get heated to their respective temperatures for the cover and absorber. So, this in general has a bearing on the operating period. One thing we will consider in detail when we talk about the utilizability concepts You may wonder, let the efficiency of a collector 1 be 72%, efficiency of the collector 2 be 36%. Okay. So, now this is, let us say, R s 5000 per meter square, this is R s 2500 per meter square. I have deliberately concocted these numbers. The efficiency is half, the cost also is half. So, if I require 10 square meters of this I may require 20 square meters, which may be approximately the same cost, except the second one may require higher piping, higher land area, etc. But somehow we can discount it the cost, and you may say it even only 2000 rupees, and the additional piping cost, even if it is considered, they will be comparable cost. Now, do you go for this or that? So, apparently let us say my initial investment is the same, okay, for a given amount of energy apparently based upon the efficiency. But the issue is really, if it is required to deliver some T minimum, let us say 60 degrees centigrade, the collector with the higher efficiency not only delivers at higher efficiency, but operates over a higher period of time, whereas the collector with the lower efficiency will operate less period, because this will be having a higher critical radiation level than this one. So, my T 1 to T 2 operating period will be larger, consequently total energy gain will be higher, not only in proportion to the efficiency, but also because of additional time that it operates. So, this is a very important issue which we will deal in detail. Then, instead of having a standard testing procedure we have discussed, typically the solar rating insolation being more than 700 watts per meter square, preferably conducted around noon time, keeping the angle of incidence as small as possible or as near normal incidence as possible, and best to measure with the pyranometer mounted on the collector surface itself. So, now you will find that Q is AC FR into IT tau alpha minus UL into TFI minus TA, and we have determined from the efficiency equation by TFI minus TA by IT versus efficiency, one line. Of course, this is beyond the operating condition, it may not be a linear variation anymore, and so this is typically FR tau alpha, and the slope of this line will be minus FR UL. So, you conduct the efficiency test and you will have the collector parameters FR tau alpha and the slope FR UL. Though there are 3 FR tau alpha and UL, they occur only in pair of FR tau alpha and FR UL throughout this course or in general in solar energy. Now, this is from the this equation, which is basically derived in 1942, Hotel Wheeler Bliss equation, though there have been some modifications in terms of f r, f dashed, etc., is the single most commonly used equation in the solar energy literature, and it will be used in the simulations for the collector, applying it over the time period that is required. So, what we shall do now is briefly consider few other geometries. First, liquid heaters. Suppose you have like this, that is the absorber with the tubes on the top soldered or welded with the bond, good bond. Compare this whatever we have considered earlier like this. So, some people argue that the tube is directly exposed to the solar radiation. So, that will be at a higher temperature, thereby making it more efficient, but others may say that this is directly also will lose heat by radiation. And of course, here because it does not come into direct contact with the heat losing surface, U L is U T plus U B, and the collector efficiency factor is given by this is very similar to what we have worked out. The notation remains the same. What needs to be perhaps reminded is H is the heat transfer coefficient inside the tube, and F is the fin efficiency, and F dashed, U L, D, W, they remain the same. W is the center to center distance. Between the tube and the tube. This is the way we have also defined when we were considering the tubes at the below the absorber plate. So, again my fin efficiency remains the same. So, F dash is different expression, tan H m into W minus D by 2 by m into W minus D by 2, where m squared is U L by k delta. Okay. So, what we had done, we will call it arrangement 1, this is arrangement 2, and we will go to arrangement 3. The regular classroom heat transfer fin and tube arrangement. This is insulated at the bottom. It may have 1 or 2 glass covers. and there is a heat transfer coefficient H, and of course, U T and U B. If you have this arrangement, U L is, though it is obvious, we will write it, because there are cases when it is not, and F dashed is 1 upon W U L by pi d H plus W by d plus W minus d into F. So, F is the fin efficiency, H is the heat transfer coefficient, as we have been defining n number of times. Now, these are the three configurations. Again, F turns out to be the same. So, definition of F remains the same. However, your F dashed differs for these three configurations. Now, it would be interesting, or you have this as an exercise for configuration 1, configuration 2, configuration 3. So, let U L K delta and D be the same. So, compare F dashed. So, I am having the same overall loss coefficient, same material thermal conductivity, same thickness and same diameter tube, and but since my expressions for F dash are different, the values of F dash will be different. So, you can compare analytically in simply what all you have to do is F 1 dashed minus F 2 dashed and F 2 dashed minus F 3 dashed. So, you will find out F 2 is greater than F 1 or F 1 is greater than F 3, etc., and you can say that this configuration is superior. The other method is simply calculate for a given material say copper or mild steel or steel aluminum with W d delta being same. One of the ideas is you go through any typical book. Of course, we shall solve the problems. You can typically say take 1 meter wide by 1.5 meters long, right, and 9 tubes, let us say 25 mm dia. So, accordingly you find out what should be the number of tubes are approximately, it may be 9, W and D is everything is given. So, for that you can compare which one is better. The question comes, I really have no answer because I have not done it exactly this way. So, if you find, for example, configuration 1 of f dash is more than f dash of configuration 2, suppose. So, your UL is same, K is same, delta is same, everything is same. Why is this so? Now, in this analysis we find that which geometry is better. In that we are making a assumption subconsciously, same bond conductance and same thickness is geometric factor, W also is geometric factor, but UL is same. This need not be, because the exposed areas are different. So, my UL may be slightly different. So, consequently, even under those conditions, it will be nice in case you can establish one configuration is superior to the other configuration, whether it is analytically or through examples. So, next time we shall consider some more configurations for the air heaters that should be bringing us close to the theory of flat plate collectors coming to a conclusion. Thank you.